Seth was worried that somebody would have escort him out of the building before his session would be complete. And I have a similar feeling today because I'm going to be talking about data science. And I've been an application developer all my life, all my career. And even if I wanted to, I could not pretend to be a data scientist. I am, however, a software engineer who's been deeply interested in machine learning, and especially machine learning's application in software development. And that is primarily because I think of machine learning as another form of programming. It is different from your traditional programming, where somebody gives you a requirement, you design the system, and then you go about writing the code. That's what you do traditionally. But in machine learning, you take those requirements and you give it to a machine, and then machine generates a program for you. Now, the requirements can be in the form of, here's some data, this is the input, this is the output, or it can be in form of constraints. And the program that the machine learning is generating looks quite different from a program that you and I write using C# or some other language. This program could be millions of numbers, which require a lot of compute capacity to run, but that's fine. With the advent of cheap computing resources, it is quite easy to run these programs. In fact, the developer cost is the predominant cost in a software development project. So let's get started. I'm going to show up the first slide here. This is, of course, the rich, diverse Azure platform. We are going to focus right in the center of this slide here, the analytics and the IoT. You see the machine learning piece right there. So if machine learning has these characteristics, it can be effective with things like voice recognition. It can be effective with driverless cars, image processing. And we are talking non-trivial image processing. We are talking about trying to identify thousands of unique objects across millions of images. If it can be effective with that, it can adapt to changing conditions. It can solve problems with little and incomplete knowledge, and you'll see an example of that, handle large data sets with anomalies. And if you look at these items here and the characteristics of a machine learning generated program, it seems to me that these are the things that we run into as software developers all the time, right? We are required to write programs with little and incomplete knowledge. We handle large data sets with anomalies. The part that I wish we had would be that I wish our programs got better with time. I don't know about you, but my programs certainly don't get better with time. In fact, they go out of vogue every time a new JavaScript framework gets released. So if machine learning can do all of these great things, why can it not do software development? And that is the fundamental question behind this talk. It turns out that there's a long, rich history of machine learning being applied to software development. If you go through a lot of journals and articles, you will find a rich history of this. And I want to motivate this by showing you a few examples. So if you can predict a stock price, or you can predict a failure, you can certainly predict fault in a software program, or you can do estimation. You can also do program induction, where you give machine learning a bit of data and have it generate a program. And I have a very cool example of this. You can also reverse engineer an existing program. You can transform an existing program. So you have a program that works perfectly, but is sequential, and you want to take this program and make it a parallel program so that you take advantage of the better compute resources available on the machine. You can also synthesize test data. So much like we took some data and created a program out of that, this is exactly the reverse. You give it a program, have it analyze the logic in the program, and come up with some test data that you can apply. It can be used in knowledge management. So you are trying to keep track of recommendations and trying to keep making the search better and things like that. So there are a number of uses, turns out, of machine learning in software development. Okay? And what we are going to do for the remainder of this session is take 3 examples and look at them in detail. But before we look at more detailed examples, let us talk about the tool that I'm going to use for the rest of my session. The tool happens to be Azure Machine Learning Studio. If you're already familiar with that, then the next few minutes might be a bit of a repeat for you. But if you have not looked at machine learning at all, I'm going to give you just enough information for you to make sense out of the rest of the demos that I do for you. Okay, so let's look into the Azure Machine Learning Studio. So what you see here is something that you have seen already. This is the Azure portal. I am dialed into the machine learning portion of the Azure Learning Studio. And the thing I'm going to do next is open up an experiment. And by the way, I'm going to use this term interchangeably. When I talk about machine learning algorithm or experiment, I'm going to use this term interchangeably, as I said. I'm going to open up this machine learning studio, or ML studio in short, and try to create these experiments. Okay, so what we're going to do here is let's create an experiment from scratch, just so you get a feel for the tool. So I'm going to create an experiment, and I have a choice of selecting from a number of experiments that Microsoft has made available and others have made available. I can just go choose that. But in order to bring out the power of this tool, let's just go with a blank experiment. And once this blank experiment comes up, you will see a template appear on the screen. And what this template is really is a consistent blueprint for almost all the experiments that you're going to see. So we start out with some data that we are going to use to train. Then we have some pre-processing that we may want to do to the data. And then we split the data. And this is a common paradigm. We split the data into two. We take one split and use it to train our algorithm. And we drag and drop an algorithm here in this box. And Microsoft has made available a rich set of high-quality algorithms that I can drag and drop. But if I'm not quite happy with what I have here and I want to bring my own algorithms, I can certainly do that. So once I've trained my algorithm, the next thing I want to do is I want to evaluate or score how well my algorithm got trained. So now remember the split, we took part of that to train. The other part goes into testing. We then score our algorithm, and then we evaluate the efficacy of the algorithm and see how well it did. So that's generally what we do when creating an experiment. Let's take a one step further here, and let's actually build out an experiment just so you have a sense for this tool. And I was thinking about what example should we build, and in the end, I ended up deciding an example which is well known in the machine learning community. We are going to build a neural network to identify handwritten digits. And why did I choose this example specifically? For three reasons mainly. One is it is a well-known sample, so the training data and test data is available directly inside the machine learning studio for me, so I can simply drag and drop it. That's one reason. The other reason is that given that this problem is well described, today we are going to take an algorithm and drop it and then adjust some values, and that's all we will do. But if you get interested in this and if you want to really look at a detailed bare metal implementation, you can find a C# implementation of the same experiment that you can go walk through, look at the math behind it, etc. And the third reason is it is quite easy to run. So this made it a good example for me to use. So let me go find the training data set, and this data set is available right inside the studio, as I said. I'm going to drag and drop the training data first, and then I'm going to drag and drop the test data next. Okay. The next thing I'm going to do is I'm going to drag and drop a bunch of activities. So the first activity that I want to bring in is the training the model. Let's just bring that here, and it will show us an error right now because it's not connected. That's fine. I'm going to also bring the scoring activity. Remember, we need to figure out how well our algorithm is doing. And the last thing I want to bring in is I want to bring in an evaluate activity. Okay, so I want the evaluate activity, just drop it here, and don't worry about the errors. We will get rid of the errors soon. So I have some training data available, and this training data is then going to get connected right here into the trained model. One thing that is missing is we are missing our algorithm, and I told you I'm going to be using a neural network. So I'm going to drag and drop this neural network here. And what we're going to do here is, let me just move this up a little bit. And I'm going to take this neural network and feed this into our training model. Okay. And I'll give you a cartoonish description of neural network. Think of neural network as a collection of nodes which are connected, and there are weights assigned to these interconnects. And by adjusting the weights of these interconnects, you are essentially modeling a piece of logic. And I realize that's rather abstract definition. So let me go to the slide for a second. So here is a very simple and yet useful neural net example. And for the history buffs out there in the audience watching this, this model was first described in 1943, and it is interesting. It is called a binary threshold neuron, and in fact, it influenced von Neumann when he was designing the universal machine. So you have a very simple neuron with one input, one output. And by the way, the name neural network is inspired by how our brain works. There's no direct connection. It's just an inspiration of how our brain works. So the brain is filled and jam-packed with neurons. These neurons connect into something called the synapses. And when we learn new things, these synapses adjust, and that's how we learn. And that really has influenced this design here. So I have a neuron which is in green here. This is that binary threshold neuron. It gets input from two other nodes here, A and B, and then I have some weight associated with that. So A and B can get values 1 and 0. And this is useful because it is actually implementing a logical AND. And if you understand this, you can then project from here and see how a neural network can train to do more complicated, difficult things. So right here, I can get a 0 or a 1. And based on the weights, I calculate the input. The input happens to be the weight multiplied by the input, and then I aggregate across that. And then once I calculate the input, I have a very simple threshold logic. If the weight is greater than 3, output is 1. If not, the output is 0. And you do the math, but ultimately, this neural net is doing a logical AND operation. Okay? So keep this in mind. Let's just go back to our studio. So I brought in the neural network here. And let's just click on this for a moment. And you can see on the right-hand side, there are a bunch of knobs and parameters that we can turn. And rather than adjusting them, remember our previous neuron was just input and output. It did not have any hidden nodes or layers in between. Rather than fiddling with all these values, I'm just going to type in a script here. And let's just bring this up here. And I'm going to type in the script, okay, rather than trying to do this manually. And this script is known as NetSharp. And there you have it. You have a gotcha question. Next time you're interviewing a C# developer, ask them what NetSharp is. Well, NetSharp is a C#-like language that is described in this neural network. Okay, so I have this neural network described now. Let's just go ahead and connect our training model to the scoring model here. And then what we can do here, the scoring model evaluates our algorithm against the trained model and the test data. So let's also bring the test data. And finally, let's connect the scoring model to the evaluate model. There is, of course, still an error here. It is asking us, what do you want me to train on? And well, I want you to train on a certain column called label. And let me just find that. There you have it. I can now simply select this, and hopefully our error goes away. So this is a very simple, well, it may be simple because of the algorithm, but the algorithm itself is quite complex, and you can see that I have two hidden layers, and I'm going to go ahead and run this, okay? And this can take a few minutes to run, and we will come back to this in a moment. But this gives you an intuition for how this tool works, okay? Now that we have completed the prerequisites, let's start drilling into our 3 scenarios. So let's go back to the slides. The first scenario that I want to talk about is the ability to derive a functional specification from existing data. Remember, I talked about inductive programming, the ability to induce a program from a little bit of data. In fact, even before we talk about reverse engineering legacy code, let's look at a fun example, something that you may have used but not realized that is connected to machine learning. So I'm going to bring up Excel here, and I'm going to show you a couple of examples. This is a feature called Flash Fill, my favorite feature. I'm going to add a new column. So a bunch of data. I'm going to insert a new column here. And what I'm going to do here is I'm going to insert a little bit of data, 413, and all I'm trying to do is I'm going to copy that number, except I'm going to add hyphens to those numbers here. Okay? So make sure I didn't make a mistake in typing. So 413 -664 -341. Okay. Now, you and I, developers, no problem. We can write some string manipulation and get this hyphenated number easily represented. But imagine if you're not a programmer. Then coming up with that program may be hard. So this flash fill capability is essentially you're telling the output and you're getting the input and you are telling machine learning to come up with a program. So now I'm going to go to the next cell and I'm going to invoke flash fill, which is the shortcut is Control E. So I do that and there you have it. What has happened here is under the covers, flash fill invoked a number of routines and I provided a very little data. Remember, just one data. It took that data, tried to induct a program from that, but then it's not quite sure what it has to do. It ran multiple programs against the data that is available in the spreadsheet, and it chose the one that it had the highest confidence for. Okay? So, very interesting example. Let's make it a little bit more interesting where the data is insufficient for training the first time around. So I'm going to go ahead and insert another column here. And let's just give ourselves a little bit more space. And because I'm a bad typer, I'm just going to copy things from here rather than type. And I am going to copy right here. And let's just take a moment to think about what's happening here. For some silly reason, I want to give all my users an email address with lastname.middlename with outlook.com. Okay, that's what I want my program to induct. So this is my output. Here's my input. Let's just go ahead and run flash fill again, which is Control E. And it, of course, does something interesting. Now, let's look at this. There's a slight problem with this code. You can see here that, when I did not have the middle name, it still inserted a period right here, similarly here. But also notice that it did something intelligent here. It appended an AU for users, which had an AU email address. So I don't know if that's right or not, you decide, but it was intelligent enough to go figure that out. Now, since I did not give this algorithm enough information, I can simply go in now and say, hey, you don't need to put this period if the middle name is not there. So I go change that and I come out of that cell and notice that now algorithm got smarter and it also fixed the other entry. So it's learning by data. So here's a cool example. So in this example, we had a little bit of data, but oftentimes we are trying to run into a situation where we have some sort of a legacy code. It is a critical business code. Unfortunately, there is no existing documentation or the existing documentation is poor, out of sync. How do we derive a functional specification in those instances? So it turns out that since we have that executable code, maybe we can invoke it a bunch of times, get our training data and our test data, and then try to train an algorithm to sort of mimic the behavior of this legacy routine. Okay? So I can certainly do that. In fact, what we did here is we took a COBOL program, not very complicated, but just to run through this experiment. I took this COBOL program, invoked it a bunch of times, and then took that data set and moved it to a machine learning experiment. So let's just go back to machine learning here, and I'm going to bring up this experiment. And since we created one from scratch, I'm not going to build this out all the way through. And I'm just going to, in fact, just show you this in existence here. So here is my data that I got by running that legacy routine and collecting the input-output values. Let's just visualize it. And you will see that I have a bunch of original sales price, and the outcome is the sales price. Okay, so I'm calculating the sales price by applying some discounts. Okay, so I ran this 500,000 times. I got some input-output. And now what I did was I normalized this data. Once again, the same pattern, split this data into two. Let's just move the cursor here to the left so you can see it better. And then I took a neural network algorithm and I trained it using that data. And then once again, we scored that algorithm using the test data, and then we evaluate it. Let's just go ahead and take a look at the results here. Let's go ahead and visualize this. And you can see here, this is the original price. This is what our legacy routine would return. And this is what our algorithm is going to return, or is returning once it is trained, I should say. You can see here that algorithm got trained pretty well. You can see that output is close. I understand that there is difference and you don't want to run your business on this, but you get the idea. And we did not really try to optimize this neural network by adding hidden nodes and things like that. So we could have done better if we wanted to. Then we went back and started looking at our COBOL routine and said, maybe this routine will do better when have an algorithm that is based around decision trees. So that's what we did. We took this algorithm once again, and in this experiment, we added a decision tree based algorithm. So one of the advantages, and this is why I think this is a tool that we developers need to understand, is this tool allows us to drag and drop a number of different algorithms and then see which one is more effective. And there's a very nice workflow that you can find in the Azure machine learning documentation that talks about how do you go about finding these algorithms. And not only that, you also have the ability to sweep through parameters. So all of these algorithms takes a bunch of parameters and you don't know which one is the right parameter. So rather than trying that manually, you can drag and drop an activity called the sweep parameter activity, which will sweep through a range of values and see which one works best. Okay? I forgot to mention this in my previous example. Once my experiment is ready and I really like it, I can right-click this here and generate a web service out of it. Okay? That's how easy it is to integrate that web service into your code. So think of that as a reuse opportunity. In fact, I think of it as a reuse plus opportunity where you can go and take these high quality routines, adjust them to your needs, and then enable them through a web service model. So let's look at the results of the decision forest regression. Exactly the same model here. And let's look at this code here and let's visualize the results. And you will see that this algorithm is quite well suited. Original price, sales price, and this is what the trained algorithm returned. As you can see, it gets really, really close. Okay? Now, I don't want you to run away from this presentation and say, hey, I found this magic wand to transform this legacy code into some machine learning experiment. Legacy code is far more complicated. You don't always have input-output. You don't have all the documentation, and these programs are highly coupled, which means they're dependent on data structures and global variables and things like that. But that's a problem that the community and the industry needs to solve. We are motivating this point of using machine learning for these kinds of problems. Let's just go back to our slides. The next example that I want to bring up is if we can predict many different things, and machine learning has proven to be very effective at predicting, why can't we predict software faults? And in fact, that's the focus of this scenario. The idea is really simple. We want to be able to predict that this module that we are about to write or embark on has a higher likelihood of faults because it matches another program that had similar characteristics. That at a fundamental level what we are after. Now keep in mind that there is a trade-off between how quickly you can detect an error and what is the overall accuracy of this algorithm. Keep this in mind. So when you evaluate the effectiveness of a fault prediction algorithm that you set up, be sure to look at this trade-off and looking at both the values effectively. So much like we use, if we were doing a stock prediction, you would take into account various parameters, and we call them features. For predicting software faults, turns out that the features that you would use would be things like this. You want to use cyclomatic complexity. You want to use essential complexity. You want to use the Halstead unique operators. Maybe you want to use the total operators and things like that. So these are kind of parameters or features that would go into training an algorithm to be able to predict fault. Let's go back to our machine learning studio, and let's just bring up this software prediction algorithm here. And I'm going to drill down into it a little bit. And this diagram looks very busy, and I'll explain why this looks busy, but fundamentally it is no different from our previous experiments. I start with a data set. You're probably wondering, where did I get this data? Well, NASA has published some really interesting data sets where all of these features were measured against how likely that a fault were to occur. So I went and grabbed that data set. But if you think about it, we actually have lots of rich data that we are collecting. If you're using Team Foundation Server, for example, there's a lot of data being collected. And if not, I think we should collect more data because it's going to become important. And once again, we split the data, send it to an algorithm, train our model, score it, and things like that. So you see that there are a number of different algorithms here that we have. And I wanted to give you a sense for how the data science process works, and I want to take this opportunity to show you that. As I said earlier, the software fault prediction is a well-known field. Lots of people have worked on it for a number of years. Earlier on, people started thinking about using logistic regression to predict software faults. But then they wanted to do something better. Then they said, maybe we should use something called the Bayesian belief networks. And the idea behind the Bayesian belief networks is that you have these interconnected set of nodes which are connected because they have some kind of a causal relationship, and then you have a probability of occurrence of that. It turns out that Bayesian belief networks are better at predicting software faults. But then we also found out that not all of these features have a causal relationship. McCabe cyclomatic complexity is not directly dependent on an Halstead number of arithmetic operators for this example. So then the data scientists started thinking of other algorithms. Maybe they thought, maybe we can represent this data that we've collected. We can start splitting that data, and then we can have a tree representation of that data that represents the rule to predict a fault. But then one tree will be too biased. Let's just get a random collection of trees, and that's where you get the random forest algorithm. But then somebody said, well, the random forest, we can do one better by sort of proportionately distributing the data. So you have a number of cases of false positive and true positive cases. Let's just distribute that evenly. And then we came up with this random, or I should say balanced random forest. So what I want you to take away from this model is the data scientists are constantly improving these algorithms. And we as software developers can benefit from their work. And hopefully these algorithms become available to us in Azure Machine Learning Studio. If they're not, you can certainly go out and pull an R module and bring that in your studio and then work with it. So that's software fault prediction. Let's just go back and see if our neural network did indeed complete. Yes, it indeed completed, the neural network that we built at the beginning of this session. Let's just go and look at how well our neural network did. And we will visualize the results here. And this will bring up something that is referred to as the confusion matrix. And so you don't get lost. I'm back to my first experiment. Remember, we dragged and dropped and built this experiment. And this was designed to identify handwritten digits. That was our problem, not a trivial problem. And we took this algorithm and then we trained it on the MNIST data. And here are the results. And you can see here on this axis, you have the actual digit. And on this axis, you can see what the algorithm predicted. And you can see it did pretty well. In all cases where 0 was sent in, 99.1% time, the algorithm got it right. It did not get it right in certain cases, like it thought it was 2 for 0.1% times. It thought that it was maybe a 6.1% time. And what is interesting is it never thought that it was 1 or 3, and that you can imagine a 1 or 3 will never look like a 0 because there's no circle there. But overall, our algorithm did pretty well. And this is just a 2-layer network. We can certainly do more things here to improve the accuracy even more. Let's just go back to our third scenario, which is about deviation analysis, and my favorite scenario. I'll tell you why. So here's the third scenario, and here we talk about automatically detecting performance deviations. And this is my favorite scenario because it illustrates why machine learning is going to be so important in the coming years. There's no question that we are generating more data. And to be analyze this data, we need some automated ways to analyze this data. So here is an example to motivate this. So we have an application that we run nightly builds on. Once the build is successful, we run some smoke test. If that build achieves a certain quality of metric measure, we then automatically kick off a load test. We collect a lot of data. We dump that load test results into some sort of a repository. And here's what happens. Unless the application has come to a screeching halt, nobody is going in and taking a look at that data. And that's problematic because your application performance may not have moved a whole lot, but there may be some kind of a trend that is emerging that may prove to be expensive later on. So wouldn't it be nice if there was an automated way to sort of analyze this results as they are coming in. So it turns out, and there's a lot of work that is done, and I reference that work here, it turns out that a lot of performance data is highly correlated, which means if you have a performance counter like total processor time versus total privilege time, it is highly correlated. So what you want to do is you want to sift through these results and you want to idealize them, which means you want to narrow them down without losing a significant characteristic of that data. So you want to boil it down. The way you do that is using something called an unsupervised learning. Why unsupervised? Up until now, we knew the right answer. We told the algorithm, here's the right answer, wrong answer, right answer, wrong answer. In this case, there is no right or wrong answer. We are telling the algorithm to go look at the data and go figure out some trend in that data. So we use k-means clustering in this example. And once we have clustered that data, and essentially we have idealized it or created a digital signature, we can then plot it on a line chart. And then we can very quickly look at that results and say if the performance is going up and down. I'm going to show you this experiment, but I'm not going to run this for you because this experiment is incomplete, and I'll explain to you why. So let's come out of this and let's just bring up the third performance deviation analysis experiment. And we take a bunch of performance data here, much like we have done in the past, and then we run some script. And I should point out that as developers, this is of interest. I have a bunch of algorithms, but I can certainly drag and drop an R activity or a Python activity and customize it. So this gives us a nice way to massage the data. So we massage the data. And then here's the k-means clustering. And this is the part which is not complete, and we need to do more work. And we didn't think of it initially, but then we went back and we realized we needed to do more work. What is happening is we are now clustering this data across multiple performance counters. But it turns out that not all performance counters have the same scale, so our results will be skewed. So we need to find a way to normalize this data before this experiment will make sense. Nevertheless, I just want to walk you through the steps. Once we have clustered this data, we can come in and take these clusters. Now we have this idealized data. And then we can then, using some R scripts, plot that on line charts, and this gives us an overall trend for where that performance is moving up and down. So let me go back to the slides here. And let me bring up this picture here. Since I didn't show you this experiment in action, I can show you this in a diagram. We start out with the baseline test. We do some data prep. We generate a signature for each run. And so we have essentially simplified this data, and then we plot it on a line chart to see how the performance is going up or down. So with this, we come to end of this session. And I have a bunch of resources here that you may find useful. There's a book by Dr. Zhang, which is the Advanced Machine Learning Applications in Software Engineering. I learned a lot from that. I think you'll enjoy that. There's also a free ebook about Azure Machine Learning. It's a great book as well. There are a bunch of helpful links that I have added to this slide. So I hope you are motivated to use Azure Machine Learning in your projects, and you think of it as a programming paradigm that makes it possible for you to build your applications quickly. Thank you for watching, and if you have questions and want to continue this dialogue, please look me up on Twitter. My Twitter alias is VLaley. Thank you.